I'm guessing that many of you think I'm a pizza fanatic after the conversation we had in the previous lesson. And you'd probably be right. I do love pizza. But I think pizza slices are the perfect analogy when we come to the subject of adding and subtracting fractions. And that's the conversation we're going to have today. Now, for those of you who aren't pizza enthusiasts, let me suggest that you think about maybe a pumpkin pie or a lemon meringue pie or some other thing instead that can be cut up into individual pieces of the same size. That's going to be what we'll want to have in mind as we talk today about adding and subtracting fractions. Now, to start off this conversation about adding and subtracting fractions, imagine that you and I are at a large party where several pizzas have been purchased. Now, don't worry about the toppings that are on each one. Just think of them as cheese pizzas. There are people in lots of different rooms in this party, so pizza boxes have been scattered throughout the house for people to get their pizza. By the end of the evening, there are pieces of pizza in some of these boxes, and you and I are now in cleanup mode, trying to pick everything up at the end of the party. We carry these empty boxes out to the garbage, and then we bring the partly filled boxes to the kitchen to put the pizzas together. Or if you want to use a bigger word, to consolidate the boxes so that we have as few boxes as possible at the end of the night. It turns out that this consolidation, combining slices from separate boxes into a smaller number of boxes, is exactly what's going on when you and I add fractions. I'm not kidding. That's exactly the idea that we should keep in mind as we talk about adding fractions today. So let's look at a basic example just to see the idea behind adding two fractions that have the same denominator. Here's the example. Let's calculate 3/8 plus 4/8. Now, the scenario I want you to imagine is thinking about this pizza and thinking about two pizzas that are of the same size that we've cut into 8 equally sized slices. Now, what does 3/8 then stand for? Well, it stands for a box that contains exactly 3 of these slices of pizza. In other words, 5 of the slices have been eaten, but 3 of them remain. We started with 8 slices in the box. We now have 3 slices in the box, so the box is now 3/8 full. Okay, now what does the 4/8 then represent? Well, it represents another box, if you want to think of it that way, that once had 8 slices in it, but 4 of the slices have been eaten, and so it only contains 4 slices in that box. Well, I have one box with 3 slices in it, which contains 3/8 of a pizza, and I have another box that contains 4 slices, and so it represents 4/8 of a pizza. So, what does 3/8 plus 4/8 then represent? It represents you and me consolidating those 2 partly filled boxes of pizza into one box. And whatever our answer is, will be how much of a pizza is in that one box when you and I are done. So, when you put the 3 slices into a new box, and you put the 4 slices in with those 3, you'll have a box, just one box, with 7 slices in it that come from an original 8-slice pizza. So, what is 3/8 plus 4/8? Well, it's represented in that one box with those 7 slices, and it's exactly the fraction 7/8, or we could say 7/8. And so 3/8 plus 4/8 really is 7/8, or 7/8. That's pretty cool, I think. Once you look at this story problem with this pizza, which I'm dwelling on quite a bit, it really demonstrates what we do when we add two fractions that have the same denominators. We simply add the numerators, put that new number as the numerator of a new fraction, and just keep the same denominator that was present in the original 2 fractions we started with. It's that simple as long as the denominators are the same. Now, let's try another one of these calculations of 2 fractions being added together. This time I'd like you to think about how to do the problem. Here it is. I want us to add 3/17 plus 8/17. go ahead and pause the lesson as needed and do that problem yourself. Okay, since the denominators are the same, they're both 17, we know the answer will be a fraction with that same denominator of 17. We simply then look at the numerators and we add those together. That would be 3 plus the 8, which gives us 11, and that 11 is the numerator of our answer. And therefore, 3/17 plus 8 over 17 is equal to 11 over 17, and we're done. Now, I'd like us to look at one more example like this, and it may be that you're thinking, do we really have to look at lots of examples that are the same kind? Well, it looks like this example is exactly like the previous two that we've done, but it actually has a slight twist. So I want us to do this one so we can see what that twist is like. Here's the problem. Calculate 2/9, or 2 over 9, it's the same thing, plus 4/9. Go ahead and do that yourself, and then we'll come together. Now, if you've done that problem, you look first at the denominators. That's what you need to look at first anytime you're adding these kinds of fractions together. And now I want us to look at the problem. I hope you worked it through and saw this added twist that we needed that was not in the previous examples. So let's look at this problem now together. The two fractions have the same denominator. It's a 9. And that means that the answer we're going to have will also have a denominator of 9 in it. Well, at least to start. Just work with me on this as we go together. Now, the numerator of my answer, since the two denominators are the same, is just the sum of the two numerators that we started with. That would be the 2 and the 4. When I add 2 plus 4, I get 6. Using that 6 as my new numerator and the 9 that we had in the denominator, I see that my answer is 6 over 9. Now you might be tempted to say, so that's the end? The answer is 6 over 9 and I'm done? Well, that would be okay to do, but now I want you to think about this twist with me. Everything we've done so far is correct, but if you look at 6 over 9 for just a minute, you realize that it is not in reduced terms. Now, in the previous examples we've done in this lesson, I didn't stop to make us think about reduced terms because I didn't want to throw too much at you at once. And it turns out in the previous examples, the final answers were already in reduced terms. You can go back and look at that if you'd like. But here, my answer of 6/9 is not yet in reduced terms. And you always want to do this. You want to look at a fraction answer and see if it's in reduced terms. Reduced terms are the best, if you will, as we talked about in our previous lesson. So, 6 and 9, what kind of common factor do they have? Well, both of them are evenly divisible by a 3. 3 is the common factor between 6 and 9 here. And so I need to divide a 3 out of the numerator and out of the denominator in order to get this fraction into, hopefully, reduced terms or lowest terms. Now, since 6 divided by 3 equals 2 and 9 divided by 3 equals 3, I know that 6 over 9 is the same as 2 over 3 once I've canceled out those 3's in both the numerator and the denominator. And so 6 over 9 is equivalent to 2 over 3, or 2/3 if you will. And my question now is 2/3 in lowest terms? Well, sure it is. 2 only has a 2 and a 1 as factors, and 2 definitely does not divide the 3 in the denominator, and so I know that 2/3 is my reduced answer. Now, let me make two quick comments here before we move on to a slightly different topic in this lesson. First of all, I'm sure that some of you would say that 6 over 9 would have been perfectly fine for you, so why in the world would we worry about this reducing? Well, I can understand this, but you need to know that there are lots of practical reasons why you don't want to leave the answer as 6 over 9. For example, if this quantity, 6 over 9, represented, let's say, a number in a recipe that had to be measured in a measuring cup, I can almost guarantee that 6 over 9 will not be one of the labels on the side of the measuring cup, but 2/3 will be, because it's reduced. And to get practical in a very different way, on some standardized tests, the answer of 6 over 9 isn't even going to appear as a choice if you're doing a multiple choice problem, but 2/3 will. So there are lots of reasons, in fact there are lots of other reasons, to finish the problem we just did by getting that fraction in reduced form. These are just a couple I want you to keep in mind. But there's another thing you might want to notice in this example. It turns out that the fractions that we started with, 2 over 9 and 4 over 9, are both in reduced form. But the answer of 6 over 9 is not. So what's my point with this comment? Well, my point is that you can actually start with two perfectly reduced fractions which are already in lowest terms, and when you add them, you can end up with an answer which is not in lowest terms. So you always have to stop before you finish a problem that involves fractions and ask yourself whether you need to reduce that final answer. This is a step that you will want to build into your routine anytime fractions are involved in the problem. Okay, I'd like to turn a quick corner now and mention subtraction of fractions just briefly. When it comes to subtracting two fractions that have the same denominator, it turns out that almost exactly the same steps have to be used as we saw with the addition problems that we just did. You just have to remember that you're subtracting instead of adding, but the same kind of steps will come into play if the two denominators are the same. So with that in mind, I'd like to look at the following example. Let's just quickly calculate 7 over 10, or 7/10 as some people would say, minus 3 over 10, or 3/10. Now, the first thing you should be doing anytime you're adding or subtracting fractions is to look at the denominators. The denominators are the key in the first place. So I look here at the denominators and I see that they're both the same. They're both 10. And that tells me that my answer will have a denominator of 10 as well, unless I have to do a little bit of reducing at the very end. So all I need to do now is figure out the numerator of the answer. Well, since those denominators are the same, and that's the important thing to look for first, all I have to do is subtract the two numerators, and that amount will be the numerator of my answer. So I simply do 7 minus 3, and I get 4. And that means that the numerator of my answer is 4. And so the denominator is 10. My final answer is 4/10. Well, it's not exactly my final answer. It's equivalent to my final answer, but 4 over 10 is not in lowest terms. So let's get that reduction going. Let's reduce 4 over 10 into lowest terms, and then we'll be done. I see that 4 and 10 are both even, so I can divide a 2 out of the 4, and I can divide a 2 out of the 10. 4 divided by 2 is 2. 10 divided by 2 is 5, and so 4/10 is equivalent to 2 over 5, or 2/5. That fraction is in lowest terms, and so my final answer here is 2 over 5. Now, let's look at one more example of this kind before we work on some problems where the denominators are not the same. Here's the example I want us to look at. Let's calculate 15 over 4 minus 9 over 4. And why don't you look at that first, and then we'll come back together. Now, first things first. The first thing you want to look at is the denominators. And in this case, the denominators of the two fractions are the same. That is fabulous. They're both 4, and because of that, it makes the problem very straightforward to do. The answer for this problem is also going to have then a denominator of 4. And next, did you notice that both of these fractions are actually improper fractions because the numerators are actually larger than the denominators? Well, is that something we should worry about? Absolutely not. We can go through the same steps that we've gone through already in the previous examples in order to finish this problem as well. Since the denominators are the same, I simply subtract the numerators, and in that case this would be 15 minus 9, and that amount is equal to 6. That 6 is my new numerator, if you will, the answer numerator, and so my answer is 6 over 4. Now, we got to think about two things before we keep going. First, is that answer reduced? I know I'm going to keep asking you that over and over, and in this case, the answer is no. That fraction is not reduced because 6 and 4 are both even. Well, if you divide out a 2 from both the 6 and the 4, you'll be left with the fraction 3 on top and 2 on the bottom, or 3 halves. So that's one thing we should always check. So my answer can be written as 3 halves, and it's a perfectly good answer. Now notice, though, that that's still an improper fraction because the 3 is larger than the 2. If you did not want an improper fraction as your answer, you would need to convert it to a mixed number. And since the 2 goes into 3 exactly one time, and it has a remainder of 1, we know that 3 halves is the same as 1 and 1/2. And so we could write our final answer either as 3 over 2, or 3 halves, or 1 and 1/2. Okay, now I'd really like to turn a corner, which for some of you might have caused you trouble in the past. And here is that corner, and it's a very important one. What happens when the denominators in an original, let's say, adding or subtracting problem with fractions are different? As I always like to say, don't worry, I'm going to show you the step-by-step way to get through that kind of an issue. It's really not that bad. The whole idea is to force those denominators to be the same, and then we know how to handle those kinds of problems. So let's start with a pretty simple example where the denominators are different, so I can walk you through the idea. Let's calculate 2/3 plus 1/4. Now, just like with the previous examples, the first step I always need to do is look at the denominators. You always need to focus your attention on those denominators anytime you're adding or subtracting two fractions. Well, here the denominators are different, and I did that to us on purpose so we could see what to do. We're not going to throw up our hands. We're not going to quit. We can handle this. The basic idea is like the opposite of putting the fractions in lowest terms. We're actually going to sort of build up the denominators, if you will, so that they're actually equal to one another. Here's the idea. We need to ask ourselves this straightforward question. What is the smallest number that both the 3 and the 4 will divide? The 3 and the 4 are the denominators that we had in the original problem. This smallest number that both 3 and 4 will divide is going to be called the least common denominator for this problem. Okay? And let me give you a basic way to figure this out. Why not start listing the multiples of one of the numbers, let's say the 3, and then ask which one in the list is also divisible by 4. Let's do it quickly. The multiples of 3 are 3, 6, 9, 12, 15, 18, and so on. We know that 3 divides all of these because they're the multiples of 3. Now, which one of those numbers is the smallest one, which is also divisible by 4, or has 4 as a factor? Well, it's definitely not the 3, nor is it the 6, because 4 does not divide 6 evenly. What about the 9? Well, 9's not even even, so 4 definitely doesn't divide that. What about the 12? Yes, the 4 does divide the 12 evenly. And now we know something. The smallest number that has both 3 and 4 as a factor is 12. So what do? Well, here's what we do. We now know that we can convert 2/3 and 1/4 into fractions, which have 12 as their denominators. Then we'll have the same denominators in both of our fractions, and then we can finish the problem the way we finished all the other examples we've done in this lesson. So that's excellent. So now what I'm going to do is basically undo the fact that 2/3 is in lowest terms by multiplying both the numerator and the denominator of that fraction by the same number so that the denominator changes from 3 to 12. I'm basically undoing the reduction of the fraction. Well, what do I need to multiply 3 by in order to get 12? The answer is 4. So what we're going to do is multiply both the numerator and the denominator by 4, and we're going to turn that fraction into 8 over 12. In other words, 2 times 4 is 8, and 3 times 4 is 12. So 8 over 12 is an equivalent fraction to 2/3, and notice that I've now forced the denominator to be 12. That's what I wanted. The numerator, by the way, just comes along for the ride. It's the denominator here that I wanted to force to be a 12. So now, I want to think of this 2/3 as 8/12 or 8 over 12 instead. Okay, and they're equivalent, So I can easily do that. If you're not sure that they're equivalent, remember that cross-multiplying idea that we did in one of our previous lessons. Now, let's convert the other fraction that we had, which was 1/4, into a fraction that also has a denominator of 12. So here's the question to ask. What do we need to multiply the denominator of 4 by in order to get 12? The answer is 3, because 4 times 3 is 12. And notice here again, it's the denominators that are our focus. They are dictating the action of this problem. The numerators just sort of come along as they do. So I'm now going to take 1/4, multiply both the numerator and the denominator by 3, and I'm going to get 1 times 3, which is 3, and 4 times 3, which is 12, and I'm going to basically convert 1/4 into 3/12. And now guess what? We took that original problem, 2/3 plus 1/4, and we've now rewritten it as 8/12 plus 3/12. It is a perfectly equivalent version of the original problem. In fact, whatever answer we get now will be exactly the same as the answer we would have gotten with the original fractions. Well, but the beauty is I now have two fractions that have the same denominator. They both have a 12 in their denominators. I know how to handle that. I now just add the numerators. 8 plus 3 is 11. And so my final answer is 11 on top over 12 on the bottom. And guess what? That's really the answer. It can't be reduced any further. We're done in this case. The original problem's answer is 11 over 12. Now, I'd like to look at another problem of this type just for some practice, just to make sure we're on the same page. So let's look at it together. Well, let me suggest you look at it first, and then we'll look at it together. Let's calculate 5/6 plus 3/8. Now, what's the first thing we should look for? You have to look at those denominators. That's the first thing that we have to focus on, and they're different. So we need to go through this process of finding the least common denominator in this problem so that the denominators become common or the same across both of the fractions. Let's write down the multiples of 6, and then we'll see which one of those is the smallest one that also has 8 as a factor. Well, the multiples of 6, 6, 12, 18, 24, 30, 36, and so on. All right, those are all divisible by 6. Now, 8 definitely is not a factor of the 6, because the 6 is too small, and it's also not a factor of 12. 8 does not divide 12 evenly, or without a remainder, if you want to think of it that way. 8 also does not divide the 18, but 8 does divide the 24. And so now what I know is that my least common denominator, the denominator I want to go for now, is actually a 24. Okay? We've now shown that the 6 and the 8, which were the original denominators, can both be lifted up, if you will, or expanded up to a 24, because 8 and 6 both divide the 24. And so 24 is what I want to use as my least common denominator. Now, the next thing we need to do is convert the 5/6 and the 3/8 into fractions whose denominators are both 24. Again, focusing on the denominators, that's the key here. So, what do I need to multiply the 6 by in order to get 24? Well, the answer is 4. So I'm going to multiply the 5 and the 6 by a 4, and that's going to give me 20 on top, because 5 times 4 is 20, and 24 on the bottom, because 6 times 4 is 24. That fraction, 20/24, is equivalent to 5/6, but it has the right denominator. And we could check that equivalency with our cross-multiplying if we wanted. I'm not going to worry about that here. Let's move to the 3/8 now. What do I need to multiply the 8 by in order to get it to be a 24? Well, the answer is 3, because 8 times 3 is 24. So I'm going to multiply the 3 on top and the 8 on the bottom by the common 3, if you will, and that's going to give me 9 on top over 24 on the bottom. And that is my new version of the second fraction in this problem. So 5/6 plus 3/8 has now been converted to 20/24 plus 9/24. And what have we done? we've gotten a common denominator, the same denominator in both fractions, and that makes this problem very straightforward. I just add the numerators now. 20 plus 9 is 29, and so my final answer is 29 over 24. Now, I should point out here that subtraction problems with fractions that have different denominators work the same way as these addition problems. We have to work at getting those denominators to be the same, and then we just subtract the new numerators. So, I suggest we now work on a problem that's got some subtraction built into it as well. In fact, I suggest we do something ever so slightly harder. Well, harder is probably too strong a word. Let's do something with a bit of a twist. Let's do a problem that has both an addition and a subtraction mixed together. Here's the problem. Calculate 1 over 5 plus 5 over 6 minus 3 over 4. Now, I can hear some of you saying, whoa, wait a minute. This is way too tough. How in the world do I handle this mixture? Don't worry about it. We're just going to work one piece at a time, working sort of left to right, if you will, just attacking the problem a little bit at a time. So let's first figure out what 1 over 5 plus 5 over 6 is, and then after we get that answer, we'll subtract the 3 over 4. So let's do the 1 over 5 plus 5 over 6. I need to get my common denominator here because the 5 and the 6 in the two denominators are different. The multiples of 5 are 5, 10, 15, 20, 25, 30, 35, 40, and so on. Which one of these is the smallest that is also divisible by the 6? Well, you can walk through the list yourself if you'd like, but the answer here is 30. And so 30 is my least common denominator. Now, I need to convert that 1/5 to a fraction with 30 as the denominator. And when I do that, I'm going to multiply both the 1 and the 5 by 6. And 1 times 6 is going to give me 6 on top, and 5 times 6 is going to give me 30 on the bottom. So I have that fraction converted with no trouble. Now, what about the 5 over 6? Well, I've got to get a denominator of 30, and so I need to multiply my denominator by 5. And if I do that, then I have to multiply my numerator by 5 as well. 5 times 5 is 25. 6 times 5 is 30. And so that fraction, 5 over 6, is the same as 25 over 30. And so I can rewrite 1/5 plus 5/6 as 6 over 30 plus 25 over 30. It's a perfectly equivalent way of writing the problem, but now the denominators are the same, which is exactly what I wanted. And so once that's happened, I just add the numerators, and 6 plus 25 is 31. So this part of the problem is exactly equal to 31 over 30. Now, to finish the problem, I need to find 31 over 30 minus the 3/4. Remember, there was a subtraction at the end of this problem. Oh no, I don't have the same denominators again. I've got a 30 in one of the answers, or one of the fractions, and a 4 in the other fraction. Well, what do? Same game. I need to get a common denominator, and I'm going to start by writing down the multiples of 30. 30, 60, 90, 120, and so on. Which of these is the smallest number that is also divisible by the other denominator, which is 4? Well, it's not 30. You can try that. You can divide 4 into 30, but you'll get a remainder. You'll get a remainder of 2. What if you tried to divide 60 by 4? Well, in fact, 4 does divide 60 evenly. There's no remainder. You can check that with long division if you'd like. And that means that I want to convert 31 over 30 minus 3 over 4 into a problem with two fractions with a denominator of 60. Okay. We can do this. We've now done a few of these in this lesson. Let's do this one here. To convert 31 over 30 to a fraction with a denominator of 60, I simply need to multiply both the top and the bottom number by 2. 30 times 2 is 60. That's going to be my denominator. And 31 times 2 is going to be 62, and that will be my numerator. Notice again throughout this lesson, we've been using our skills in multiplication and so on quickly. And so knowing those basic facts is still very important. We've converted that first fraction to 62 over 60. What about 3 over 4? Well, how much do we need to multiply 4 by in order to get to 60? Well, the answer is 15. 4 times 15 equals 60. And so I'm going to multiply the 3 and the 4 by a 15 in order to get an equivalent fraction. 3 times 15 is 45. You can do that with long multiplication if needed. And 4 times 15 is 60. And so that second fraction is 45 over 60. And so my problem has now been rewritten as 62 over 60 minus 45 over 60. Same denominators, so I simply subtract the numerators. 62 minus 45 equals 17. And so my answer now is 17 over 60. And that's the answer. That's the answer to that original problem. It looked a little bit scary at first, but it turns out that this fraction, 17 over 60, is the answer. Now, before we finish that problem, we should ask ourselves, is that in lowest terms? Well, I've kind of rigged the answer to a bit to help us. 17 only has 17 and 1 as its factors. And I can tell that 17 doesn't divide 60 evenly, and therefore I know that this fraction actually really is in reduced form. Final answer, 17 over 60. Well, today we've worked through several examples of how to add and subtract fractions, both that have common denominators already in them, as well as different denominators. I hope you'll work through these kinds of problems in the workbook as well. Practice can never hurt when it comes to these kinds of problems. And next time, we'll continue to talk about fractions, but we'll talk about multiplication and division.